In the last lecture, we had looked at different crystal lattices and we were looking at the cubic lattice, the BCC lattice, the body centered cubic and the face centered cubic. And then we came to the diamond lattice, which can be described as two interpenetrating FCC lattice, where the second FCC lattice, which is shown in green, is displaced with respect to the first along the body diagonal. And you can describe this diamond lattice with a cubic unit cell, which is your conventional unit cell, not the primitive unit cell. This is a conventional unit cell with lattice constants A, and there is a 2-point basis, namely you are describing it with cubic unit cell with 2 lattice points per unit cell. Okay, and these 2 lattice points are at 0, 0, 0 and A by 4, A by 4 and A by 4. Of course, in diamond lattice, for example, in the carbon lattice, all of these atoms are identical, they are not blue and green, they are not separate. For example, in silicon and germanium, this is also the case, and you get this sort of a structure. But if these atoms in this diamond lattice of the two interpenetrating lattices, if they have different set of atoms, for example, the blue atom could be zinc and the green atoms could be sulfur, then you get the zinc blende zinc blende crystal structure. This is again the diamond lattice, which is made up of two interpenetrating lattices, but now the atoms which sit on these two different interpenetrating FCC lattices are different. On one of them you can have zinc, on the other hand you can have sulfur, and you will get the zinc blende crystal structure. And different types of compounds actually crystallize into this sort of a structure, and again there are some important, very important semiconductors which crystallize into this structure, like gallium arsenide, gallium phosphide, indium antimony and so on. So, these are the structures, these elements actually crystallize into the zinc blende structure, which is just a variant of the diamond lattice structure. Another structure which we come about in nature, and large number of different compounds actually crystallize in this, is a hexagonal lattice or a variant, a slight variant of it. What is a hexagonal lattice? A hexagonal lattice or a hexagonal Bravais lattice is formed by this hexagonal collection of points which are arranged on the edges of a hexagon. You have these points which are arranged at the corners of a hexagon. And this is important. If you recall, I had shown you a honeycomb lattice structure. The honeycomb lattice structure is somewhat like this hexagonal lattice, but with the central lattice point missing. Here you have the central lattice point. Okay. So, the hexagonal lattice structure is formed by a set of points. The hexagonal Bravais lattice is formed by points which are arranged at the corners of a hexagon. Again, the lattice parameters and the lattice constants are the same. Okay. So, you have this 2-dimensional hexagonal Bravais lattice, and now on top of these atoms or these lattice points, you can place another at a distance c away. Okay, these could be A and A, you can place another at a distance c away and you will get the hexagonal Bravais lattice. Now, if you see, these points are sitting directly above the lattice points on the hexagonal lattice below. Okay. And you can describe your unit cell with your hexagonal Bravais lattice. Okay. So, these form now your lattice vectors A1, A2 and A3. Okay. And with this you can describe your, just like you have the cubic unit cell and BCC and FCC are described, the variants of cubic cell, the BCC and FCC are described in terms of the cubic lattice. In the case of hexagonal lattice, different variants of the hexagonal lattice you can describe in terms of the hexagonal Bravais lattice. Okay. And these are the primitive lattice parameters for this hexagonal lattice. Let us go further, and first let us consider the hexagonal lattice system. So, suppose I have these balls, okay, you can think of these spheres, okay, and if I join them, then these spheres will arrange themselves into a proper hexagonal lattice So, this is the 2 dimension. So, on the plane of the paper you can take these balls all of same diameter and you can collect each of them. Okay. You have seen this in while playing carom also, that if you take these small cylinders, your coins, and if you arrange them, then they will form a hexagonal lattice. Okay. So, that is a hexagonal Bravais lattice that you get on a plane. Now, if you notice that there are gaps in between these balls will certainly not join up with each other, and there are gaps that you get in between the balls. Okay. Now, one can identify 2 different types of gaps. One is the B type of gap, this is a B type of gap, and this is of course a B type of gap, this is also a B type of gap, and these are C type of gap. Now, we want to make a 3-dimensional structure. I have made on a plane a hexagonal lattice. Now, if I want to make a 3-dimensional hexagonal lattice in the 3rd dimension, what I will do? I will put my 6 set of balls over this point A. Okay. These point A, which are the center of these balls, I can place another collection of these balls exactly in the same tight configuration of these balls. If I take another arrangement of these balls and place it directly over the point A, all these points A, such that they completely match each other, the lower and the upper layers are all matching over, sitting one on top of each other, then I will generate the 3-dimensional hexagonal Bravais lattice, which I have shown you here. This is the 3-dimensional hexagonal Bravais lattice, where over the point A I am stacking the layers one on top of each other. So, this is known as AAA stacking, where all the layers are being put over the points A. Now, I have identified these gaps in between, B and C type of gaps. Okay. Now, over the B type of gaps, if I place my set of balls, now the next layer of balls, if instead of placing it over A, I start placing it over these B gaps, only over the B gaps, and then the 3rd layer which I put will be above the A points. The type of structure I get is like this: A, this is the A layer, of course this is the lowest A is the A layer. The B atoms or the B lattice points are put over these points, only over the B points, we do not put any points over C, and then the 3rd layer that you put in. So, these are the 2 A layers, they are directly one on top of each other, and the B point is slightly displaced. This type of structure is AB, AB, AB structure, and this is called as a hexagonal closed pack structure. Hexagonal closed packed lattice. It has the layering which is AB, AB, AB type. Now, as you might have guessed that I can put points over B, but so I can make a layer by putting points over B. I can make a 3rd layer by putting points over C and then point A. So, I can create layering where I have A layer, I have these balls which are put over the B layer, and I have balls which are put over the C layer, and then again I repeat over the A layer. Namely, these two are exactly on top of each other. B layer is slightly displaced and the C layer is again displaced in another direction. So, I have stacking ABC, ABC, ABC. I can put these balls one on top of each other and I can create a different type of a stacking of these lattice points, and this sort of a stacking actually leads to very surprisingly to the FCC lattice. Okay. So, the FCC lattice has ABC, ABC, ABC stacking. If you stack these points which are shown here in this ABC, ABC, ABC configuration, you will land up with an FCC lattice. But if you do AB, AB, AB stacking, okay, with these balls, you will get an HCP lattice. So, hexagonal close pack lattice can be actually described by a conventional unit cell of an HCP lattice is nothing else but the hexagonal Bravais lattice, which is this hexagonal structure AAA type of a stacking, but it now has an additional layer in between. This layer, which is the B layer, has been put in between the two A layers, and so this leads to your hexagonal close pack structure with has a basis of 2 atoms per point. You can show that again this has a basis of 2 atoms per point. Its conventional lattice is the hexagonal Bravais lattice with AAA type of a stacking, and you have put in a B layer in between that will give you the additional atom in that layer. And there are different types of materials again which actually crystallize into the HCP structure. Quite a large number of elements crystallize into this structure, for example zinc, magnesium and so on crystallize into your HCP structure. So, this is also a very well known structure seen in nature. Another structure which is commonly seen in a variety of compounds is the sodium chloride structure. If you recall, the diamond structure was 2 FCC lattices which are displaced along a body diagonal, and the second lattice is actually kept at 1/4 along the body diagonal distance. The sodium chloride structure is also FCC structures, but they are interpenetrating, they are not along body diagonals, okay, and they are this sort of a structure where the green atoms is the sodium atoms and the yellow atoms are chlorine atoms. If you look at the distribution of the chlorine atoms, you can certainly make out an FCC structure. If you look at the distribution of these chlorine atoms, this certainly looks like an FCC structure. They are sitting at the corners and on the faces of a cube. So, this is your FCC structure. And if you look at the distribution of the sodium atoms, which are these green atoms, okay, the sodium atoms which are the green atoms, these also sit on a FCC structure, where if I draw the next set of atoms, for example these are the next set of atoms or the lattice points, then you can see these green atoms are actually sitting, they also form an FCC structure. The green atoms, if you forget about the yellow atoms and only look at the green atoms, then these are also FCC. So, you have chlorine atoms and you have sodium atoms which form a lattice by interpenetrating with each other. On one of the lattices sodium atoms sit, on the second lattice chlorine atoms sit, and this sort of a sodium chloride like structure is displayed by variety of materials. For example, MgO is a popular material used in research in condensed matter physics. MnO is also a popular material which is studied. Potassium chloride solids and potassium bromide solids. Of course, NaCl is from where the original structure is defined and derived. Lithium hydride. So, all of these materials actually have a structure which is exactly like this. Sodium chloride is just to define this type of a structure, 2 FCC lattices which are interpenetrating with each other in this way, but with 2 different atoms on the 2 different FCC lattices. Just like you had the zinc blende structure, here you have the sodium chloride structure which has 2 interpenetrating lattices interpenetrating in a particular way. The cesium chloride structure is another type of a structure where you have atoms which are sitting on the corner of a cube. It is very much like a body centered structure, but you have atoms which are sitting on the corners of a cube and another different atom which is sitting at the center of the cube. Okay. So, for example, chlorine could be sitting in the center and cesium is on the corners of the cube. There is 1 atom per unit cell. So, you have 1 cesium atom and 1 chlorine atom per unit cell. And again there are a variety of materials which can form this sort of a cesium chloride structure. So, you can have BCC structures where all the atoms are exactly identical, or you can have a BCC structure in compounds. You can have BCC structure where 1 atom is sitting on the corners and another type of atom or another element is sitting at the body centered position, and this gives you your cesium chloride structure. So, these are some of the important structures which I have defined to you, namely your cubic structure, simple cubic structure, BCC structure, FCC structure, the diamond structure, the zinc blende structure, your sodium chloride structure, cesium chloride, hexagonal Bravais lattice and the hexagonal close pack structure. These are some of the structures which are displaced by a variety of elements or compounds, and they can fall into one of these crystalline types or the lattice types.